Okay, guys, welcome back. We're now going to go ahead and go to the bottom of the green sheet, the green proof. So the proof that we just completed with the stacked triangles. There is a question stuck at the bottom. It's called bonus, but let's be really honest, that wasn't bonus. That's something we covered in class, and you guys should be responsible for being able to reproduce or kind of handle on the quiz you'll have on Friday. So you have to prove the sum, the addition of any two even numbers will be even. Now, again, something that we know logically, something that we can certainly produce a lot of examples for, but in terms of proof, we have to show it happens for every case at the same time. Now, we can't accomplish that by simply showing a bunch of examples because there's an infinite number of examples. We just can't do it. Um, Although an example might actually give us a place to start, and that's where I'm going to start here. So if I just pick any two even numbers, any two kind of random even numbers, let's say 4 and 6, I have to show the result will always be even. In this case, of course, it's 10. I know it's going to be true. So the trick is really how do I take this spot right here, this little slot in the addition, and have it represent every single even number at the same time. In the same way, how can I take this spot in my calculation, the 6, and have it generalized to every single value at the same time? Um, there's an easy way to do it. Certainly, we're going to use some variables, but be careful. If I just choose like a random number, like k, a random variable, excuse me, like k, and even if I come over here and say, as part of our givens, that k is an integer, that doesn't actually get me anywhere because an integer could be odd or even, and this calculation has to be even. Now, we do have a way to do this, and instead of calling this slot right here just a k, we can call it a 2k. Because even if the number chosen to be k is odd, let's say like 3, multiplying by 2 makes it 6, it's even. That's something that we know for sure happens. Um, Now, what we have to show over here, or do over here, is the same kind of thing. We have to generalize this spot in the calculation to be something that's also going to be even all the time. Now, we cannot use k anymore because if I have 2k plus 2k, that's implying that I'm adding the same number or a number to itself. That's no good. I can, however, use a different variable. So let's say like 2m. Again, I have to kind of mention over here in my givens that m is an integer. Okay. But in the end, this is a calculation. Now, I have to show that it's equal to an even number, not just 10, but any even number. But again, um, we already have a good sense of what that should look like. 2 times an integer. In this case, I'm just going to use I to represent integer. Okay? But this is what we actually have to show. We have to prove that this equation is actually true, hence the question mark. Now, to prove this is true, all we have to do is visually confirm it's true. In other words, I have to make this left-hand side say 2 times an integer, just like the right-hand side does. Now, this doesn't look too daunting. I just have to kind of use my algebraic skills to make this work. I should notice that there's a 2 in this term and also a 2 in this term. If there's 2 in both terms, I can factor that out as a common number, as a common factor, if you will, hence term factor. So that's what I'm going to do. I'm going to take the 2 in each individual kind of term and write it out in front and create a distribution problem behind it. So I'm going to ask myself, 2 times what spot here gets me at 2k? Of course, the answer is k. And then I'm going to add that to 2 times what gets me 2m? Of course, the answer is m. This is actually the conclusion of my proof. This is actually all it took. I had to make the left-hand side look like the right-hand side. The right-hand side has a 2 times an integer. Well, here's the 2. Okay? Now, this integer, I don't care about the value. It just has to be an integer. Well, if k is an integer and m is an integer, then certainly k plus m is an integer as well. So in the end, I do end up with 2 times an integer is the same as 2 times an integer, hence the proof that if I choose any k, any m and any k at all, um, that no matter what happens, it'll end up being multiplied by 2, hence it's going to be even. Right? So this is a good proof.